Numerical integration using Simpson's rule. So unlike the other methods that we've seen previously, using rectangles to approximate the area underneath the curve, this method uses polynomial curves in order to get the value of an area within a bounded interval, of course. The formula is the following: fx equals delta x divided by 3 multiplied by fx0 plus 4fx1 plus 2fx2 plus 4fx3 plus 2fx4. It is like a sequence, a pattern, plus at the end fxn. As you notice, only the first element and the last element for fx are not multiplied by anything, but in the middle for fx odd, x1, x3, x5, they are multiplied by 4. For the others, they are multiplied by 2. This is the pattern that we need to notice. How it works: you multiply delta x divided by 3 by all the following elements. For the first and last points, you don't multiply by anything. For the odd numbers or odd values of f, you multiply them by 4. For the even position indexed values, you multiply by 2. The formula for that is the following: fx equal delta x divided by 3, you multiply this number by everything on the inside, times fx0 plus a sum from I equal 1 to n minus 1 to the one before the last, fxi multiplied by 2 times I modulo of 2. As you notice, for the odd place values like fx1, fx3, etc., the value of I, since it is odd, I modulo of 2 would give you 1. So 1 times 2 plus 2, that would be 4 times fxi. For the even placed numbers, the numbers with even index, like fx2 for instance, 2 modulo of 2 gives you 0, 0 times 2 0, and what remains is plus 2, because the first one has cancelled out, so you still have 2 times fxi, which is this product here. Writing the program for Simpson's method. Let's start at first with the polynomial function, double f double a double b c and x. This is the function we're talking about. It has a form of ax2 plus bx plus c. Return for each x the value of f, which is a times power x2, which is x to the power of 2, plus b multiplied by x plus c. Then the function that will evaluate the integral using Simpson's rule. Double Simpson double a double b c, and the boundaries double b1 double b2, finally n, which is the number of slices, for this integral. Int I double delta is equal to b2 minus b1 divided by n, the number of slices. Double x equal b1, this is the first boundary, the first point we start with. Double s is initiated at 0, that's the sum that will keep adding up the areas of the respective slices underneath the curve. For I equals 0, I less than n, I plus plus. If I equal to 0 or I is equal to n minus 1, in other words, for the first and the last element, we don't multiply f by anything. S plus equal f a b c x. Else, s plus equal to f a b c x multiplied by I modulo 2 multiplied by 2 plus 2. So if I is odd, I mod 2 has the remainder of 1 multiplied by 2 plus 2 is 4. So you get 4 times fabcx. Otherwise, if I is even, then this product is 0. What remains is 2. And 2 alone is multiplied by fabcx. Finally, we need to add up x with a step of delta. And outside of the loop, we need to multiply this sum by delta divided by 3. Return s. Going to main, double sum equals Simpson. That's the name of the function. 1 0 0 0 2, and the number of steps is 100. Let me explain. So a alone is equal to 1, but bc equals 0, which is the function y equal x squared, and the bounds of this integral are from 0 to 2. The number of slices is 100 to get a little bit accurate result. Printf at last \n area of x2 between 0 and 2 %f sum. Let's see the result. 2.56. Remember, the accurate value is around 2.66. Alright, but if I increase the number of steps, you get a more accurate value. So let's try it for, say, 10,000. That's 10,000. And this is a more accurate value.